Cell 1. In this cell, we're diving into the flight operations for three key airports in the New York City area: EWR, LGA, and JFK. This exploration is crucial because it allows us to understand not just how flights are operating, but how weather conditions might influence those operations over the coming week. The first step in our process will be to gather the flight data, focusing on key metrics such as the number of flights scheduled or those that have already arrived. Alongside this, we'll track average delays, which will provide insights into the reliability of these airports during different conditions. An important aspect here is the creation of a binary label for major delay. This label will help us quickly identify significant disruptions, which can be critical for both operational decisions and passenger planning. Next, we plan to merge our flight data with hourly JSON weather forecasts. This requires us to ensure that the data aligns perfectly based on the time column. The aim is to construct a unified dataset where each row represents a specific airport and hour, encapsulating all relevant flight metrics alongside the corresponding weather information. It's important to note that aligning these datasets can be tricky. We'll need to pay attention to time zones and ensure that all timestamps are consistently formatted to prevent any mismatches. By the end of this cell, we expect to have a detailed view of flights against the backdrop of weather forecasts, setting the stage for our analysis. As we move into the next cell, we'll likely be applying this merged dataset to explore trends or correlations between weather conditions and flight delays, enabling us to derive actionable insights that can inform both operational strategies and traveler information. Cell 2. In this cell, we're fetching weather data from New York City using the OpenMeteO API and processing that data into a format that's easy to work with. This step is crucial, as understanding the weather is vital for many applications, from planning outdoor activities to analyzing climate trends. First, we set the geographical coordinates for New York City, specifically its latitude and longitude. With these variables defined, we construct the URL and parameters needed to make a request to the API. The parameters indicate that we want hourly forecasts for temperature, precipitation, and wind speed over the next 7 days, specifically tailored for the Eastern time zone. Once we make the request using the requests library, we ensure the call is successful by employing error handling through raise for status. If there's an issue, like a network problem or a bad request, this will let us know immediately. After confirming the request went through, we extract the data into a structured format. Here, the essential hourly data points are captured in a data frame, which sets the stage for easier analysis. Importantly, the time column is converted from a string format to a more manageable date-time format, allowing us to perform time-based operations later on. To get an overview of the data we're working with, we check its dimensions and display the first handful of entries. A common pitfall when working with web APIs is not handling potential errors in the response data, something to keep in mind as you move forward. This meticulous approach to fetching and formatting data will serve as a solid foundation for our subsequent analysis, where we might visualize or derive insights from this weather information in future cells. Cell 3. In this cell, we're creating a visual representation of the upcoming week's weather forecast, which includes temperature, precipitation, and wind speed details. This visualization is crucial because it allows us to quickly grasp expected weather patterns, helping to inform decisions related to activities and planning. The workflow begins with importing necessary libraries for data manipulation and visualization. We create a copy of the hourly weather data and ensure that the time column is in a proper date-time format. Sorting by time is essential, as it organizes the forecast chronologically, making it easier to interpret. Next, we initialize a figure to hold our plots. We start by adding a scatter plot for temperature, clearly indicating the expected temperature trends over the next week. This is particularly useful for identifying peaks and troughs in temperature, giving insight into potential extreme weather conditions. Following that, we incorporate a bar chart representing precipitation levels, which visually contrasts areas of rain against the temperature line. This dual representation aids in understanding how temperature and precipitation might interact, something that's particularly relevant for planning outdoor events. Lastly, we add another scatter plot for wind speed, further enriching the forecast. The layout adjustments, like the title and axis labels, help clarify what the viewer is looking at, and the settings ensure that the graphs display well together, allowing for easy comparison. As we move forward, the next cell is likely to delve into deeper analysis or predictive modeling by leveraging this visual output. By interpreting what we see here, we can make more informed predictions or recommendations related to the weather data. Cell 4. In this cell, we are generating synthetic data related to flight operations in the New York City area based on weather conditions. This is important because understanding how various factors influence flight schedules can help in better anticipating delays and cancellations, which is crucial for both airlines and passengers. The function begins by making a copy of the incoming weather data, converting time information for easier manipulation, and sorting it chronologically. We focus on three major airports: Newark EWR, LaGuardia LGA, and John F. Kennedy JFK. For each of these airports, we establish a baseline volume of flights that they typically handle, which serves as a reference point for our calculations. As we iterate through each hourly weather data entry, we calculate a demand pattern that peaks in the morning and evening, reflective of common travel behaviors. Weather conditions such as temperature, precipitation, and wind play a vital role in shaping our operational assumptions. For instance, colder temperatures introduce a penalty, which influences our overall flight scheduling. We utilize a Poisson distribution to simulate the number of scheduled flights, adjusting this slightly based on whether it's a weekday or weekend. Cancellations are also modeled here, as they tend to rise with more severe weather, capped at a reasonable level, to maintain a realistic scenario. In terms of operational efficiency, the mean delay is influenced by both the severity of weather conditions and airport congestion. The logic here accommodates the common observation that busy hours can exacerbate delays. Finally, we quantify the likelihood of major delays, basing this on factors like weather severity and mean delay, which adds a layer of probabilistic depth to our flight operation data. When we run this function, we get a data frame of flights, with all these important metrics captured. It's worth noting that the assumptions we made about weather impacts are simplified, but provide a meaningful baseline for further analysis. As we look ahead, the next cell will likely build upon this flight data, perhaps exploring how to visualize these operations or analyze patterns over time, equipping us with insights into the flight landscape under varied weather conditions. Cell 5. In this cell, we're merging our flight data with the corresponding hourly weather data, which is crucial for understanding how weather conditions might influence flight operations. By aligning these datasets based on time, we can analyze patterns and draw insights about the interactions between flights and the weather. First, we create a copy of the weather data frame to avoid altering the original dataset, a good practice for maintaining data integrity. We then convert the time column in this new weather frame into a proper date-time format. This step is essential since accurate time representation allows for effective comparison and helps prevent unexpected issues during the merge. Next, we perform a similar operation with the flight data, copying it and again converting the time column to a date-time format. This consistency across our datasets is key, as it prepares them for a smooth integration. The heart of this cell lies in the merge operation, where we're combining the flight data with the weather data. By utilizing a left join on the time column, we ensure that each flight entry retains its information even if there isn't a corresponding weather record. This allows us to keep the integrity of our flight data while enriching it with the weather context. Once the merge is complete, we print the shape of the resulting dataset to understand how many records we now have, and then we display the first few entries. This way, we can verify that the merge has worked as intended and check whether the weather data aligns properly with each flight entry. As we move forward, this enriched dataset will enable deeper analyses, such as identifying how weather impacts on-time performance or delays, which will be explored in the next cell. This will build on the foundation we've just established by combining these datasets. Cell 6. In this cell, we're focusing on the essential task of simulating major weather events at airports to illustrate their impact on air travel. This step is critical for understanding how disruptions can ripple through the operating environment, feeding into our eventual modeling efforts for predicting delays. The function you've just encountered is designed to inject specific weather disruptions into a dataset that represents weather conditions at various airports over time. It takes a data frame and a list of predefined weather events, each with parameters for wind, precipitation, and temperature changes at specific airports and times. The goal here is to make the model more robust by training it on scenarios that resemble real-life weather challenges. Within the function, the data frame is first copied to ensure that the original data stays intact. The time column is then converted to a date-time format for easy comparison. The function loops through each weather event, applying the specified changes in wind speed, precipitation levels, and temperature reductions. By filtering the data with a mask that looks for the appropriate airport and time period, we can selectively adjust only the relevant rows in our data frame. It's important to note some assumptions here. For instance, we assume that the weather events occur within a certain window and that all alterations can effectively simulate the disruptions without affecting other conditions inaccurately. This sort of manipulation can introduce complexities, so users should be cautious in interpreting results, as real-world weather impacts can be influenced by numerous external factors. Finally, as we look ahead, this cell sets a solid foundation for the following steps where we'll leverage these simulated weather disruptions. We'll begin to train predictive models aiming to forecast delays based on our adjusted dataset. This will create a more dynamic understanding of how various factors interplay in the world of air travel. Cell 7. In this cell, we're conducting a sanity check on our simulation results by examining the maximum recorded wind speeds, precipitation levels, and temperatures for each airport. This step is crucial because it helps us verify that the modifications we've made in the simulation are producing realistic and sensible outcomes. To dive deeper into the logic, we're using a grouping operation on our data frame. The data is segmented by the airport column, allowing us to focus on each airport individually. Within each of these groups, we're particularly interested in pulling out the maximum values for three key variables: wind speed measured in kilometers per hour, precipitation in millimeters, and temperature in degrees Celsius. This grouping and aggregation help us understand the extremes of our weather data after the simulation adjustments have been applied. By assessing these maximum values, we can identify any outliers or unexpected patterns that may emerge. It's essential to pay attention to these results because they serve as indicators of whether our simulation adjustments remained within realistic bounds. If any airport shows strikingly high or low values, it could suggest potential issues with the simulation logic, such as an error in parameter adjustments or perhaps an unrealistic environmental assumption. This approach allows us to validate our results and ensure that they make sense in the context of what we expect to see in real-world conditions. Moving forward, the next cell will likely build on this sanity check by incorporating these max values into further analyses or visualizations, helping us derive more insights from our modified simulation results. Cell 8. In this cell, we're constructing a small but realistic airport network graph focused on New York City's primary airports: Newark, LaGuardia, and JFK. The rationale behind building this graph is to illustrate how these airports are interconnected and how flight delays can propagate due to shared air traffic situations. This is crucial in understanding the dynamics of air travel in a bustling city where airspace is tightly coordinated. We begin by creating a new graph object using the NetworkX library, which is a powerful tool for analyzing complex networks. Next, we add our airport nodes, which serve as the key points of our network. Each airport represents a node in this system, building the foundation of our graph. After establishing the nodes, we connect them with edges, effectively modeling the direct flight paths between each airport. The connections are defined by the shared airspace, indicating that all the airports can affect each other due to overlapping flight paths. Once the network is fully established, we calculate various centrality measures to give us insights into the network structure. The degree centrality shows how many connections each airport has, essentially indicating each airport's immediate reach within the network. Betweenness centrality, on the other hand, highlights which airports serve as critical conduits for travel within the network. This measure reveals the potential bottlenecks where delays might propagate through the system. Lastly, closeness centrality measures how quickly one can access each airport from any point in the network, shedding light on travel efficiency. As we look at the outputs of these calculations, it's important to remember that the assumptions made here, such as the fully connected nature of the metropolitan airspace, simplify the reality of air travel dynamics. These centrality measures can inform future analyses exploring an expanded network, possibly incorporating more airports and realistic operational factors. The next cell is likely to build on these concepts, perhaps investigating specific delays or real-time data to see how they affect the centrality measures we've just defined. Cell 9. In this cell, we're enhancing our dataset by introducing features that capture weather severity and their influence on airport operations. This is vital because understanding how weather affects delays can help us better predict and mitigate disruptions in air travel. We start off with a function designed to calculate a severity score based on several weather factors: wind, precipitation, and temperature. The logic here accounts for how significant each factor is in determining overall severity. For instance, higher wind speeds and precipitation levels contribute more heavily to the score, while extremely cold temperatures impose an additional penalty. This creates a nuanced understanding of weather conditions. Next, we incorporate these severity scores into our data frame alongside other significant features. First, we convert the time data into a proper date-time format and sort our data by airport and time to ensure proper alignment of the weather data. After applying the weather severity function, we calculate average severity scores for neighboring airports, enabling us to assess how weather in nearby areas might impact delays. Static graph features are also extracted, such as the degree centrality, betweenness, and closeness centrality for each airport. These measures provide insights into how well connected an airport is within the network, potentially influencing how it reacts to severe weather conditions. We also consider temporal aspects by creating lagged features for delays and weather severity. These lags help capture the historical persistence of conditions affecting delays, offering a clearer picture of how the weather might influence future events. Additionally, we encode cyclic hourly information with sine and cosine transformations, ensuring that periodic trends are appropriately captured for any machine learning applications we might pursue later. After enhancing our data frame with these features, we ensure it's clean by removing any rows that contain missing values for lags, which is crucial for maintaining robust data integrity. In the next cell, we'll likely focus on how these features interact within a predictive model, exploring their implications for delay prediction and further refining our approach. Cell 10. In this cell, we're focusing on creating predictive models that can forecast flight delays and classify major delays. This task is crucial for airlines and passengers alike, as it can help in better scheduling and improving overall operational efficiency. To start, we define the features that will be used in our models, ranging from flight dynamics, like the hour of the day and day of the week, to weather conditions and historical delays. We then collect our target variables, which include average delay times converted to floating point numbers and major delays represented as integers. This sets the stage for our analysis, enabling us to create regression and classification models. Next, we implement a time series split method to account for the temporal aspect of our data. This approach is vital when dealing with time series data, allowing us to train and test our models on sequential splits. thereby mimicking real-world forecasting scenarios. We've employed two powerful algorithms, the Hist gradient boosting regressor for predicting delays and the Hist gradient boosting classifier for identifying major delays. Throughout our iterative process, we train the models with the training datasets and evaluate their performance on the test datasets. We calculate various metrics, such as the mean absolute error and root mean squared error for the regression model, which provide insights into the accuracy of our predictions. For the classification model, we focus on the AUC score, offering a measure of how well the model distinguishes between major delays and non-delays. After completing the iterations, we summarize the performance of our models by printing out the average values of our calculated metrics. This gives us a clear, quantitative assessment of how well our models are doing. Looking ahead, the insights gained from these predictive models can guide us in refining features further or exploring additional modeling techniques. The next cell will likely build on these results, possibly exploring how to enhance model performance or incorporate new datasets. Cell 11. In this cell, we're assessing the performance metrics of our predictive model for average flight delays, and understanding these metrics is crucial for interpreting how well the model is functioning. First, let's look at the mean absolute error, or MAE, which stands at approximately 2.03 minutes. This figure tells us that on average, the model's predicted delay is about 2.03 minutes off from the actual values, and a lower MAE indicates a better performing model. Next, we have the root mean square error, RMSE, which sits at 2.70 minutes. RMSE is a bit different. It squares the errors before averaging, which means it's more sensitive to larger discrepancies between predicted and actual delays. Seeing that RMSE is higher than MAE is typical, as the squaring process inflates larger errors. Both of these metrics suggest our model could use some refinement, since lower values are ideal. Moving on to the area under the curve, or AUC, for major delays, we find a value of 0.526. AUC provides insight into how effectively our classifier can differentiate between major delays and non-delays. With a score hovering just above 0.50, it indicates that the model does not perform much better than random guessing. Typically, values above 0.60 are considered acceptable, while scores above 0.80 reflect strong predictive power, highlighting that we may need to enhance the model's ability to classify delays accurately. Lastly, the R-squared value shows us the goodness of fit for the model, standing at around 0.46. This means that the model accounts for approximately 46% of the variance in average flight delay minutes. While achieving an R-squared of 0.70 or above is ideal, it's important to note that achieving a perfect score of 1.0 is unrealistic in practical scenarios. All these metrics point towards areas for improvement, and understanding their significance will guide us as we refine the model in upcoming analyses. In the next cell, we will probably explore strategies for improving these performance metrics and delve into techniques that could enhance the model's accuracy and predictive capabilities. Cell 12. In this cell, we focus on using our previously trained models to forecast delay risks for a 7-day horizon. This is crucial because understanding how various factors contribute to flight delays allows airlines to make better operational decisions and improve passenger experience. Here, we first fit our regression model to the data, targeting the average delay minutes, and then apply the classification model to estimate the probability of a major delay. The dataset we use includes a variety of features, like weather conditions at each airport, which are pivotal to our predictions. After fitting the models, we predict the average delay minutes and the likelihood of a major delay, storing these values in the data frame for further analysis. It's important to note how we incorporate not just local weather conditions, but also the interconnectedness of airports. The variable WXSEV encapsulates the severity of weather at the airport in question, combining factors like wind, precipitation, and temperature. The higher this value, the more operational stress is expected, leading to increased chances of delays or cancellations. On the other hand, WXSEV neighbors accounts for the weather severity at neighboring airports. This variable is vital, as it recognizes that delays are often contagious within a network of airports, especially in densely connected regions. For example, if weather at JFK is significantly poor, this might not only affect flights at JFK itself, but can also cause delays at neighboring airports, such as LaGuardia or Newark. The model takes into consideration these spillover effects, meaning that good weather at one airport doesn't guarantee smooth operations if another airport in the network is facing challenges. By integrating these insights into the predictions, we better reflect the real-world complexities of air travel. Looking ahead, the next cell will likely build on these predictions, possibly exploring how they can be utilized for operational strategies or generating visual insights into the data. This will provide a practical application for our forecasting efforts, further bridging the gap between analysis and actionable outcomes. Cell 13. In this cell, we're focusing on visualizing delay predictions for specific airports and understanding the relationship between actual and predicted delays, especially in the context of significant weather events. The goal here is to create a clear graphical representation that showcases how well our model performs in forecasting delays and highlights periods of major delay risk. To achieve this, we begin by filtering the dataset to isolate records that pertain to the chosen airport, ensuring we're working with relevant data. The data is then sorted by time, which is crucial for accurately plotting our predictions alongside the actual delay data. Using Plotly, a powerful graphing library, we craft a figure that incorporates three key traces. The first trace represents the actual average delay in minutes, which serves as a benchmark to evaluate our predictions. Next, we add a trace for the predicted average delays, allowing us to visually compare our model's predictions with real-world outcomes. Lastly, we include the predicted probability of a major delay, expressed as a percentage, to indicate the risk level associated with delays at that airport. As we create this visualization, it's important to ensure that each component is clearly labeled and that the layout is designed for readability, especially since we're plotting data across time. Calling attention to both the actual and predicted delays in the same graph facilitates an understanding of our model's accuracy over time. Notably, a learner should consider the potential for discrepancies between the predicted and actual delays, which could arise from unpredictable weather changes or other external factors. Finally, this cell demonstrates the effective use of visualizations to communicate complex information and lays the groundwork for further analysis. In the next cell, we might delve deeper into how these predictions can inform operational decisions at the airports, turning data insights into actionable strategies for managing delays. Cell 14. In this cell, we are transitioning into a more structured decision-making framework that integrates multiple factors impacting flight delays. This is a crucial step because it allows us to take the insights we've gathered so far and shape them into actionable predictions. To achieve this, we're synthesizing various elements we've previously analyzed. We have the point delay predictions expressed in minutes, which helps quantify how long we might expect delays to last. Additionally, we're considering the probability of major delays, giving us a sense of risk management. The inclusion of weather severity signals enables us to account for environmental conditions that could impact flights, while the network spillover signals allow us to consider how delays might affect interconnected flights at different airports. The framework will require integrating all these components cohesively. We need to ensure that assumptions such as network connectivity and weather impact are clearly stated and understood. One potential pitfall here is underestimating the influence of one factor over another. The interplay between weather and network conditions can often lead to nonlinear outcomes that are complex to predict. As we implement this decision framework, we're essentially creating a roadmap for how to predict flight delays more accurately using our established methods. We'll need to examine how these elements work together in practice, refining our approach as insights come in. Looking forward, the next cell will likely delve into the practical application of this framework, putting theory into action and showing how we can operationalize these predictions to enhance flight scheduling and management. This is an exciting step towards making our analysis not just theoretical, but directly beneficial for real-world decision-making in aviation. Cell 15. In this section, we're validating the operational performance of our predictive model, focusing specifically on how well it categorizes delays into predefined buckets. This is important because it allows us to assess not just the accuracy of our predictions statistically, but also in a manner that is actionable for operations. We start by creating a copy of our initial data frame to ensure we don't alter the raw data during this analysis. Next, we define the delay buckets, which categorize delays into 4 distinct groups: on time, minor, moderate, and major, based on the duration of delays measured in minutes. These categories provide a clearer picture that operations staff can easily understand and utilize. Once we have established our buckets, we proceed to assign actual delay categories from the dataset and our predicted categories into new columns. This step is critical because it allows us to visually compare what actually happened against our model's predictions. After classifying the delays, we compute a confusion matrix, which serves as a powerful tool for evaluating the model's performance. It gives us a comprehensive view of how many delays were correctly classified versus those that were misclassified, and highlights where confusion typically lies. The confusion matrix produced here will be transformed into a more user-friendly format in the next step, turning the matrix into a data frame for easier interpretation. As we analyze this output, it's essential to remember that while predictive accuracy is vital, the real-world implications of these classifications matter even more. Errors in these categories could lead to significant operational inefficiencies if not addressed. Therefore, as we move forward, we will delve deeper into this report to uncover actionable insights and potentially refine our predictive model based on these findings. This step not only facilitates operations, but enhances our understanding of the model's effectiveness in real-world scenarios. Cell 16. In this cell, we focus on calibrating predicted probabilities to ensure they accurately reflect actual outcomes. This step is crucial because we want our model's predictions to have real-world significance, helping us understand just how reliable these probabilities are when assessing risks. The first key action here is binning the predicted probabilities. We achieve this by dividing the predicted major delay probabilities into 10 distinct bins. Binning is essential as it allows us to categorize our predictions and evaluate their performance more effectively. In our dataset, we create a new column, prob bin, which assigns each predicted probability to one of these bins based on its value. Next, we perform a group aggregation on these bins. This involves calculating the mean predicted probability for each bin, the actual rate of major delays, and the count of occurrences within that bin. By averaging these predicted and actual values, we obtain clearer insights into how well our model aligns with reality. It's important to note that a strong model will show the predicted probabilities closely matching the actual rates of delays across these bins. However, learners should be cautious about the binning process. If not done correctly, or if the predicted probabilities are poorly distributed, this can lead to misleading conclusions about model performance. We're essentially assessing whether our calibration indicates trustworthiness. If the predicted probabilities closely align with actual rates, we can be more confident in our model. As we move to the next cell, we'll likely build upon these insights to further refine our model or explore additional factors that could affect our predictions, deepening our understanding of the risks involved. This ongoing calibration process is essential for developing robust predictive models. Cell 17. In this cell, we're focusing on enhancing our dataset with important temporal features. These features will allow us to better capture the dynamics of airport delays and flight congestion over time, which is crucial for predicting future behavior. Initially, the data is sorted by airport and time, ensuring that any subsequent calculations respect the chronological order of events for each airport. This step sets the stage for creating lagged features, which are essential for understanding past conditions. Specifically, we compute the lagged average delay from the previous time step and a lagged probability related to major disruptions. This will let us see how past delays correlate with current conditions. Next, we introduce a rolling average that takes into account the delay over the last 3 time points at each airport. By doing this, we're essentially creating a memory of congestion that can smooth out fluctuations and reveal more persistent trends and delays. Such rolling metrics can often prove to be more insightful than immediate values, as they depict the ongoing narrative rather than isolated incidents. After we prepare these features, it's important to clean up the dataset by dropping any rows with missing values. This ensures that our final dataset remains robust and ready for analysis, free from any gaps that could skew our findings. When we display the first few rows, we'll get a clearer picture of how these new features interact with our existing data, providing valuable insights. Looking ahead, the next cell will likely build on this enriched dataset, possibly incorporating these new features into a predictive model or further exploration of the patterns captured through this temporal analysis. Cell 18. In this cell, we're taking a step toward making our network graph not just a visual representation, but an actionable tool for analyzing airport delay risks. Specifically, we're calculating the network spillover risk associated with delays, which is crucial because delays at one airport can often impact neighboring airports. To achieve this, we first create an undirected graph using the NetworkX library, defining our airports as nodes, and the connections between them, weighted by their potential influence on delay propagation. The edges are given a weight that suggests how strongly a delay at one airport might affect another. In our example, Newark, LaGuardia, LGA, and JFK have established connections, each with a different weight, indicating the strength of their influence on delays. Next, we define a function named network risk, which calculates the risk for a specific airport at a specified time. As we loop through each neighbor of the selected airport, we access their associated edge weights. Then, we look up the predicted major delay probability for that neighboring airport at the same time. If a prediction exists, we multiply the weight of the connection by that probability and sum it up, thus aggregating the spillover risk. The final step applies this function across our data frame, assigning the calculated risk to a new column named network risk. This operation not only enhances our dataset, but also integrates a critical view of how interconnected flight delays are, highlighting the kinetics of air traffic. As we look forward, in the next cell, we will build upon this risk assessment by perhaps visualizing these interactions or developing strategies to mitigate delays based on our findings. Understanding these interconnected dynamics will be key in future analyses, especially when we explore real-time data or decision-making frameworks. Cell 19. In this cell, we're diving into weather stress testing, specifically simulating the impact of a snow and wind event on our data. This is crucial for understanding how extreme weather can affect operational capacity and service reliability, providing insights that can lead to better preparedness and response. We're starting by creating a copy of our original dataset, which allows us to manipulate the data without altering the initial information. The next step involves defining an event window for the storm, specifically between noon and 6 p.m. on January 16, 2026. This time frame is where we'll be intensifying our weather severity metrics. By adjusting the WXSEV variable, which reflects the severity of weather conditions, we're adding 0.6 to those values within the event window. Additionally, we're increasing the WXSEV neighbors variable by 0.4 to capture impacts from surrounding areas, recognizing that weather effects are rarely isolated. Next, we introduce a simple stress response model that integrates several factors to estimate potential delays and major incidents. The stress delay variable combines predicted delay minutes with an adjusted value reflective of weather severity and network risk, giving us a more complete picture of operational strain during severe conditions. Similarly, we calculate the stress major prob, which increases the likelihood of major disruptions, again, adjusting for the weather severity while ensuring that probabilities remain within a valid range from 0 to 1. By displaying the first few rows of our modified data frame, we can visually inspect how these changes have been implemented and what the data looks like post-adjustment. It's important to note the assumptions we're operating under, in particular that the severity ratings translate directly into delays and disruption probabilities, a simplification that might not hold true under all conditions. Looking ahead, the insights we gain from this weather stress test will inform our operational planning and resource allocation strategies in the next cell as we explore implications for real-world decision-making in reaction to these simulated conditions. Cell 20. In this cell, we're focusing on transforming predictions into actionable decisions, a crucial step in decision-making processes. The essence of this transformation lies in the decision policy function, which evaluates different factors related to stress probabilities and delays to recommend appropriate operational responses. The function examines the stress level that a given row represents. It first checks if the probability of a major stress event exceeds 3/4. If it does, the recommendation is to cancel or delay operations as a preemptive measure. If the likelihood is significant, but not as drastic, the recommendation shifts toward increasing staffing to mitigate stress levels. Next, if the potential delay exceeds 25 minutes, a suggestion for gate reassignment comes into play as a preventative tactic. Finally, if none of these conditions are met, the operation continues as normal. This logical progression ensures that we're making informed decisions based on the predictive insights from our dataset. As we move forward, we also introduce a cost-aware optimization layer. In this section, we define constants representing the costs associated with delays and cancellations. This financial perspective helps quantify the operational impact of our decisions, allowing us to calculate an expected cost for each situation. For every entry in our dataset, we derive this expected cost by weighing the duration of stress delays against the specified cost per minute, and also factoring in the likelihood of cancellation due to major stress. When we display the first few entries of our updated data frame, we can see how the decisions and associated costs play out across different scenarios. It's important to note that what we're engaging in here is known as prescriptive analytics, as opposed to mere forecasting. This kind of analysis propels us beyond predictive models into the realm of making strategic recommendations based on those predictions. In the next cell, we'll likely delve deeper into how these decisions impact overall performance metrics, or perhaps explore further optimization strategies based on the data we've generated here. Cell 21. In this cell, we're focusing on enhancing the interpretability of our data through an explanation function that breaks down key factors impacting our results. We want to understand how various elements, like weather and network risks, influence our primary metrics, which is crucial for making informed decisions based on the analysis. The logic starts with the definition of the explain_row function, which takes an individual row from our data frame and calculates three critical aspects. First, it addresses the weather's impact, scaled by a factor of 12 and rounded for clarity. This scaling allows us to interpret the weather severity in a more digestible way, making it easier to grasp its potential effects at a glance. Next, we look at network risk, which is multiplied by 8 and again rounded. This could highlight how connectivity issues might play a significant role, particularly in scenarios that rely heavily on network integrity. Finally, we don't ignore the temporal component, specifically the 1-hour lag of delays, which we include directly from the data without scaling. Then, the function is applied across the entire data frame, generating a new column labeled explanation, where each row now contains these computed insights. This step demonstrates the power of using the apply function efficiently to transform our data, allowing each entry to contribute more contextually to our understanding of the overall analysis. One key point to keep in mind is that scaling factors should ideally be backed by domain knowledge to ensure they reflect real-world implications accurately. If not appropriately chosen, these factors could misrepresent the severity of conditions. As we conclude this step, the next cell is likely to delve further into the implications of these insights, possibly leading to visualization or deeper analytical techniques to communicate our findings more effectively. Cell 22. In this cell, we're organizing our data into a structured format that makes it easier to understand the performance of various airports by calculating key performance indicators. This step is crucial because it helps us synthesize complex information into manageable insights that can be effectively communicated in reports or presentations. To achieve this, we start by grouping our dataset by airport, which allows us to examine each airport independently. The aggregation function then plays a pivotal role as we're calculating three important metrics. First, we're determining the average delay for flights departing from each airport, which can indicate overall operational efficiency. Next, we look at the probability of experiencing major stressors linked to these delays, providing insight into how frequently significant disruptions might occur. Finally, we consider the average expected cost associated with those delays, an important factor for both passengers and airlines when making travel decisions. The outputs of this cell will be a summary data frame comprising these aggregated metrics, clearly showing the average delay, the probability of major disruptions, and the average costs per airport. A learner should keep in mind the importance of ensuring the data is correctly grouped to avoid misleading conclusions. If any airport has too few data points, the averages might not reflect typical conditions, which could skew our understanding. As we move forward, the next cell will likely take this summary and dig deeper, perhaps by visualizing these metrics or comparing the performance across different airports more rigorously. This will enhance our analysis and provide a more comprehensive view of the airport efficiencies we're observing. Cell 23. In this cell, we're developing an interactive visualization using PyVis to represent the airport network with a focus on risk factors that can impact operations. This approach not only makes the data more accessible, but also allows users to engage with the information in a dynamic way, bringing clarity to complex relationships and risks. To start, we establish a specific timestamp for our analysis, which in this case is set to January 16th, 2026. The relevant data is then filtered to isolate the risk metrics associated with each airport at that moment. This includes key attributes like stress delay, major delay probability, and overall network risk. These factors will help us understand which airports might be more vulnerable and why. Next, we define several utility functions to enhance the visualization. The function for assigning colors to nodes is crucial, as it uses a simple logic based on the probability of major delays. Higher probabilities are marked with warmer colors, indicating greater risk, while lower probabilities display cooler colors, signaling a safer environment. The size of each node corresponds to the potential stress delays, scaled appropriately for clear visual differentiation. Additionally, we create tooltips that reveal detailed information about each airport, such as stress delay times and decision-making status. This makes the graph not just visually appealing, but also informative, allowing users to glean insights simply by hovering over the nodes. Moving on to the network visualization itself, we set up the PyVis environment, fine-tuning parameters to enhance user interaction and make the network feel responsive and engaging. The nodes, enriched with risk-driven styling, are dynamically added to the network, ensuring that even airports without data are represented, albeit in a muted style. Furthermore, the edges connecting the airports reflect their interaction strength through thickness, emphasizing the importance of these connections in the overall risk landscape. Finally, we render this interactive graph as an HTML file, allowing us to view it seamlessly within the notebook. The next steps likely involve analyzing this visual output, extracting insights from the relationships displayed, and possibly making strategic decisions based on the observed risks. This bridges the analysis to actionable insights that can greatly impact airport operational strategies. Cell 24. In this cell, we're developing a dynamic visualization of risk factors impacting NYC airports. This is crucial as it allows us to understand the interplay between various features like weather and flight activity, and how they collectively influence delays and disruptions. The cell consists of several key functions and procedures that work together to create an interactive network graph. We begin with defining what information we want to include in our tooltips, such as temperature, precipitation, and flight statistics, allowing the user to see the current driving factors at a glance. The Make Title Richer function serves to format this information neatly, helping users glean insights quickly. Next, we calculate the flow of risk in our network by examining the relationships between airports. This is done using the Edge Risk Flow function, which assesses the probability of a major delay for the airports involved, scaling this risk based on existing edge weights within the graph. This allows us to understand how risks flow, not just from one node to another, but how they might affect the overall network. Then, we proceed to construct the actual network visualization with the Build Pivot Network function. Here, we add nodes representing airports and visually depict their risk levels through adjusted sizes and colors. Larger red nodes indicate higher risk, whereas smaller green nodes suggest lower risk. This visual cue aids in making risk assessment both immediate and intuitive. After the nodes are set up, we loop through the edges and use our previously defined function to determine the flow of risk between pairs of airports, which creates directional edges between them. This architecture not only illustrates the current state of risk at a chosen timestamp, but also prepares us to explore how these dynamics might change over time. Lastly, we implement a drop-down widget that allows users to select different timestamps, prompting the network graph to re-render for the selected time. The ability to interact with this data enriches the analysis immensely, as users can track changes over time. As we move into the next cell, we will likely delve deeper into the implications of these visualized risks, potentially exploring predictive modeling or risk mitigation strategies based on our findings. Cell 25. In this cell, we're examining how to identify significant alerts from our stress data, focusing on airports that might be facing higher risks due to various factors. This analysis is crucial for decision-making, especially in operations where timely responses can greatly reduce risk and improve outcomes. The code begins by printing the nodes in our graph, representing the airports we're working with, alongside unique airport identifiers from the stress data frame. This gives us a quick view of our data structure, helping understand what we're analyzing upstream. Next, we define a function called Top Alerts, which takes the stress data frame, a specific time point, and optional thresholds for probability and delay. Within this function, the data for the given time is filtered from the stress data frame. After creating a copy of this subset, we calculate the percentage of major stress probability by multiplying the stress probability values by 100. This metric helps in quantifying how severe the stress is. We then look for alerts based on two critical conditions. We flag entries where the major stress probability exceeds our defined threshold, or where delays reach a certain level. These conditions highlight the airports that are experiencing either significant stress or substantial delays, which can impact their operations. The filtered results are sorted primarily by stress probability and then by delays, ensuring we prioritize the most concerning alerts for analysis. The output of this function includes several crucial columns, which provide insights into the airport's situation, such as stress delay, the percentage of major stress, and weather severity indicators. It's important to note that the threshold set can greatly influence the number of alerts generated, so it's imperative to adjust them thoughtfully. By calling this function with our stress data and a specific time, we get a structured list of the airports that might require immediate attention. This setup sets the stage for subsequent analysis, where we can delve deeper into interpreting these alerts and connecting them to practical implications for operations and management. In the next cell, we're likely to explore how these alerts can inform strategic decisions or interventions by analyzing their interdependencies or responses. Cell 26. In this final cell, we are wrapping up the work we've accomplished throughout this Jupyter Notebook. While it might seem simple to just conclude, it's actually quite crucial, as it ensures that all our previous analyses are coherently tied together and understood. As we finish, it's a moment to reflect on the data processes we've executed and the insights we've garnered. Throughout this notebook, we've navigated through various techniques, examined numerous datasets, and likely encountered both challenges and revelations along the way. This cell acts as our bookend, signifying not just an end, but also the culmination of our efforts in understanding the data. It's important to criticize and discuss the insights we've derived. We could consider what assumptions might have influenced our conclusions and acknowledge any limitations of our analyses. Throughout our journey, we've been careful to validate our findings, ensuring that the insights we gained are reliable and meaningful. Moreover, it's also a moment for you to think about the implications of the work you've done. How might these results be used in practical scenarios? Are there questions that remain unanswered, or alternative methods that you might apply in the future? By reflecting on these aspects, we not only solidify our understanding, but also pave the way for further inquiries. Transitioning into the next stage of your learning journey, it's worth considering how you could apply these methodologies to new datasets or even different contexts. The analytical skills you've sharpened here are just the beginning. As we move forward, you can take these principles and explore fresh datasets, continue refining your techniques, and perhaps even challenge the insights we've gathered with new questions and data.